Assalamualaikum and hi everyone. We are from Group 7. Today we would like to present our posters, which is the synthesis of titanium nanoparticles by pulse laser ablation method. So this project was consist of 7 members, which is the first one is me, Muhammad Faris Izwan bin Muhammad Zani, Azan Nur Ain binti Azmi, Nur Hidayatul Atira binti Jeffrey Nur Syahida binti Nur Rizan, Nur Syazana binti Muhammad Rifin, Putri Nur Amelina and Siti Nur Huda binti Zahma.
Assalamualaikum, my name is Putri Amelina and today I would like to talk about the introduction of this topic. Titanium nanoparticles are attracting considerable interest due to their unique optical and electronic properties. While several synthesis methods exist, pulse laser ablation stands out as the most promising way due to its distinct advantages. However, inconsistency in the resulting nanoparticles, which range from titanium oxide to mixed amorphous and crystalline pieces, have led to ongoing debate within the field. This work therefore aims to identify the optimal ablation parameters to control and characterize the titanium nanoparticle that are formed through this method. Next, I would like to let my friend to present their methodology.
You ever wonder how we can create nanoparticles without harsh chemicals? In this studies, let me introduce you pulse laser ablation in liquid, which is PLAR. How it works? So, it's actually a high energy laser like an NDYAG fires pulse inside the solid target submerged in liquid. The laser will vaporize the target, creating a plasma bomb that coats rapidly in the liquid, forming tiny nanoparticles. So why you use PLAR? First, there is no chemicals. Unlike the traditional methods, it avoids toxic reagent. Second one is pure product. Nanoparticles are contaminant-free. Last one is tunable properties, which is just change the laser setting on liquid to control the size, shape, and compositions.
So, in methodology, they have two steps. Which the first step is preparation of target and liquid. First, clean the titanium metal target with ethanol and DI water. Next, place the target at the bottom of the wax and fill the cuvette with 10 until 20 ml of DI water as the liquid medium. Next is step 2, which is production and catalyzation of TiO2 nanoparticle that use a pulse NDYAG laser, which are different experiments are conducted for multiple parameters such as below. And for the catalyzation, the TiO2 nanoparticle will be characterized by using EDS, FAR, PSAM, and TEM.
First, for different ablation times as shown in figure 1, at 15 minutes the solution was light blue greyish, at 30 minutes it turned from colourless to a darker blue greyish, and at 45 minutes the solution changed to an even darker blue greyish. Therefore, the optimal ablation time is 30 minutes. Next, for different laser frequencies in figure 2 with a fixed 30-minute ablation time, at 1 Hz the solution turned blue greyish, showing good dispersion of titanium nanoparticles, but at 10 Hz the solution remained colourless, indicating no effective dispersion. So the optimum frequency is 1 Hz. Lastly, for different laser focus height shown in figure 3, at the focus point, the color turned blue-grayish, but at 100 cm below the focus point, there was no color change. This is because the energy reaching the metal was reduced at a greater distance.
Now, moving on to the chemical composition of the synthesized titanium nanoparticle, we use energy dispersive X-ray spectroscopy (EDX) to determine the elemental composition. The analysis confirmed that titanium and oxygen were the major component, indicating the successful formation of titanium dioxide nanoparticle. Minor elements such as carbon, silicon, aluminium, and calcium were also detected in trace amount. These impurities are likely due to the laser beam interacting with the cuvette material during the ablation process. Next, the FTIR analysis further supported the presence of titanium dioxide. The spectrum showed a broad peak around 3450 corresponding to OH stretching from hydroxyl group, a sharp peak at 1630 for C double bond C stretching, and strong peak between 400 to 600, which are characterized of titanium oxygen bond vibration. Now, let's look at the morphology and size of the nanoparticle, which were examined using PSAM and TEM. At 90 volt, the particle were against particle, but more uniform with a smaller size range of 40 to 120 nanometers. To validate this, we use TEM imaging on the sample prepared at 900 volt. It clearly shows spherical nanoparticle with size ranging from 30 to 200 nanometers, and they were well dispersed with minimal agglomeration. So, both chemical and morphology analysis confirm the successful synthesis of spherical titanium nanoparticle with the best quality achieved at 900 volt of input laser energy.
In conclusion, this study showed that pulse laser ablation in liquid is an effective and green method for synthesizing titanium dioxide nanoparticles. The best results were achieved using 30 minutes of ablation time, 1 Hz of laser frequency, direct focus point positioning, and 900 volt of laser input energy. By using characterization technique, it confirmed the morphology, elemental composition, and the presence of titanium-oxygen bond, indicative of titanium dioxide formation. That's all from us. Thank you.